That's our module 7. And it's more exciting in a way because it has movements in it, unlike electrostatic. And then the first topic we'll cover about magnetostatics is just like we started with Coulomb's law and forces on charges. We will start talking about forces. And then from there, go to magnetic fields. Okay, so here, let's say you have a magnetic flux density that exists in space, okay? Here, unlike electrostatic, where we were talking about electric field all the time, E, and then we briefly talked about electric flux density, which was D. Here, it's a little bit reversed. We talk about B a lot, which is magnetic flux density, okay? And if you remember, H was magnetic field. This was in ampere per meter, and this was Tesla. Okay, so here we have a magnetic flux density that exists in space at some point, and then we have a point charge, Q, that is moving with the velocity of U. Velocity vector U showing the direction that this Q is moving and the speed that it's moving with, okay? Now, we can say there will be a magnetic force on this charge that is equal to Q U cross B. And this magnetic force would only exist if the charge is moving. And even if it is moving, then you'll see that, U cross B has to be non-zero for Fm to be non-zero. Okay? So, magnetic force only applies to moving charges where the velocity is not parallel to the magnetic field, okay? Why? Because if B was parallel to U, it's going to make me laugh. Okay, if U was parallel to B, then U cross B would be 0. Okay? So that's why we say that U cross B should be non-zero for the magnetic force to be applied. Now let's see. How can I find the direction of this magnetic force? Right-hand rule. U cross B. Now tell me, what is that direction here? First of all, is B going to the page or coming out of the page? Into the page. Okay, so U cross B is going to be this direction. This is going to be Fm. And it's going to be perpendicular to vector U. Okay? So what happens? If the charge was moving on this trajectory, right? Trying to move with this, right? Okay? If it was moving on that trajectory initially or as planned, right? What Fm does is that it will take Q and it will bring it a little bit higher every time. For example, when U is in this direction, again, you would solve this and then would be here. So this is the new U, and this is the new Fm. Then this is again another U at this point. This is going to be Fm. So every time the charge, instead of going directly on that original path, let's say it was going on this original path, it's not going to do that. It's going to follow this deviated route. Ask me. Ask me. What is the problem?
I'm confused how this works. Like, figure, like.
So start from the arrowhead of U. Okay? Start from the arrowhead of U. Okay? Now, B is saying you're going into the page, right? The only thing you have to do is say, this is the arrowhead. I'm going into the page.
Wait, so your thumb goes into the page and then.
No.
Your
U.
fingers. Your thumb is where FF is.
Like the palm of your hand points towards the magnetic field. Your
Yes.
thumb points towards the magnetic force. Your fingers will be the velocity.
Oh, okay.
Yeah, that's a better way. Yeah, your palm should be going this way. That's U and then FM. Yeah, maybe that way is easier. Thank you, Nice. Okay. So we got FM to be QU cross B. Okay? Now, what if we had both electric field and magnetic field? Okay? You know, you're experts. What is the electric force on this Q? QE. So we have, what is the direction of this force?
It's Q positive or negative.
Let's say Q is positive
It'll be in the direction.
in the electric field. So FE is QE. Does it depend on velocity? No. As long as there is an E and there is a Q, there will always be an electric force on it. And we just learned that there is going to be an FM here that is perpendicular, and it is QU cross B. So not only it depends on the value of the Q, it depends on the value of the field that you have there, but also the velocity that this charge is moving with. Okay? Maybe this color would be easier to read. Okay? So, if I put this charge that is moving in the existence, in the presence of the both of them, this is Q, and it is moving in U direction, then the total force on it is going to be the electric force, or the force that the electric field is applying, and then also the force that the magnetic field is applying. And now we know that this is QE plus QU cross B. That's E plus U cross B. So now, let's see. If Q was trying to move on this trajectory, right? Which way would it go? Okay, so we have FE, right? We have an FE that is going to be in this direction. And then we know that we also have an FM in this direction. Based on the value, we add them up, right? You would see that this is going to be, the total charge is going to be in, this direction. This is F total. So now what happens? As soon as it gets here, it tries to go that way. Again, that way. So again, deviation happens, but a bit faster, right? So here, the electric field and the magnetic field, would both of them deviate the path, or like they try to, how do you say it? Like steer it toward another direction. Okay, so Q would end up here instead of here. Is that clear? Right? Okay. So I just want you to remember that the magnetic force exists only if the charge is moving, and only when the magnetic field and the movement direction are not parallel, right? Okay. Now, what is the work done by the magnetic force? We found that the work that was done by the electric force, we said W of E was QV, right? That's how we translated this. We defined voltage as the work that is being done on Q. And then we said this is FE minus FE dot DL. Let me just minus FE dot DL, right? Which was minus Q E dot DL. This was the work we were doing. As long as the electric field and DL weren't perpendicular together, right? You were moving along the electric field lines, then there would be a voltage, there would be a work done, right? Now let's calculate that for FM. WM. WM, again, you're opposing FM as well, right? You're trying to oppose magnetic force to see how much work you will be doing. Or if you wanted to find the magnetic work that is being done by the magnetic force, then it's just going to be a plus, right? F dot DL is the work that a force does. Do you remember that? Right? Okay. So, what was FM? Q, U, cross B. Perfect. Dot DL. What is DL? U?
Divided by magnitude.
U is a velocity, right? So it's DL over DS. U DS. So here, let's find it. It's going to be Q U cross B dot U DS. What is this dot product?
It is 0 except they're perpendicular.
Exactly. U cross B, whatever vector it is, you know that it's perpendicular to U, right? So I'm going to call this like vector A. This is perpendicular to B and to U, right? So if A is perpendicular to U, then A dot U is going to be 0. So when the magnetic force actually changes the direction of this Q, it's not actually doing any work. It's as if the gravity work that I would be doing, just moving this in this direction, horizontal. Imagine this as my charge, and this charge is perpendicular to its force, or DL is perpendicular to the force. So just like, even though it looks like you're spending energy, you're not. For that force, you're not. Okay? Now, so we said magnetic force only exists when we have moving charge, a moving charge, right? That's the definition of currents. Currents are charges that are moving, right? Delta Q over delta T. So you can say I is delta Q over delta T. Moving charges. So a Q is going from this direction, one electron, let's say, to this direction, to this point. It's as if U is in this direction, right? Okay. So, what is the force on that Q? The magnetic force. U cross B. So here, as Nis said, palm of your hand towards the magnetic field, your fingers showing U, then the thumb is going to be showing FM. So what happens? If the 2 points of this current are fixed, what happens to it there?
Is it going to move the whole wire? Or
They're fixed. I kept it fixed.
Oh, I mean, it's going to stretch?
Yeah, just like a little bump,
Yeah.
right? So, yes, because it can't move at these points, but the force is going to try to make it like this. Or maybe more practical is the wire is going to look like this. If you have a wire hanging in the magnetic field, it starts moving in that direction. It never looks straight. And if I was reverse, it was going in the other direction, then naturally FM would be here, so the wire would get moved to this point. Good? You happy? Okay. Now, so now what do we have? We found that just like currents, just like moving charges, if you have piece of current in the presence of the magnetic field, there will be a force on it, right? So let's see how much that force is. We have a current I. We know that FM is QU cross B. We also know that I is delta Q over delta T. Now, so delta Q is going to be I delta T, right? What else can I say here? And U is dl over dt, right? So I can write it like this, that Fm is like delta Q, which is I delta T dot dl over dt cross B. This is a cross. This dt and delta t are the same, so it's going to be I dl cross B. So the force on every section of this wire or current is going to be I dl cross B. So if I had just dl here, I dl cross B. If it was here, I dl cross B, right? So if I wanted to see from point A to point B, what was the total magnetic force, then it would be, this is like a DFM, a small portion of it. FM would be the integral of DFM from point A to B, which would mean I dl cross B from point A to point B. Okay, so, but current doesn't go from point A to point B. Current goes in loops, right? It starts from somewhere, ends up to the same place. So in order to have this as a practical thing, this has to be a closed loop. In that case, if you want to find the total magnetic force on this loop of current, then you would say Fm is equal to I dl cross B on a closed contour. So this is magnetic force on a section of the wire, and this is magnetic force on the closed current loop. Okay.
Why didn't we close the contour? If we have like if A and B is a defined path that may not be straight, but if it's defined, can I just not close it?
Yeah. But if you have a closed loop, which usually happens for currents, then it has to be a closed contour that you're integrating. If it says find the magnetic force on this closed current loop, then you do it on all of the parts, which was going to be a closed contour. Go ahead.
Why doesn't magnetic force cancel out? Like if there's a wire going, current's going up like that, and current is going down like that, and you do like the hand move, it doesn't, like, don't the forces go against each other? So
We'll look at it. We'll look at it. But
Also,
yeah, yes.
okay.
Yeah. We'll look at it. Okay? So, since we started talking about current again, then we remind ourselves that we had 3 types of currents, right? Linear one, which is ideal. This is a vector. Or we have surface current density, which is ampere per meter. Remember this. This is Js, the surface current density, multiplied by ds, which is this. ds is this one. It's a length. It looks like, we don't want to call it dl because dl is a section of the wire, but ds is like a width. So the surface current density multiplied here is I is Js multiplied by this ds. If it's too confusing, don't use ds. Just say W, small. The only thing to remember is that this is a width. And current is going, it only has 2 dimensions, dl and also ds, but the current that goes through it is the current density multiplied by the width. And here, the volume current density that you're familiar with is sigma E, okay? And that's ampere per meter squared. And in order to find I here, you would say this is integral of J dot ds. So you have 2 dimensions. Does it make sense? And this is S over, this is S. And if I wanted to find I here, that would be JS dot I don't want to call it DL. It's DW, let's say. JS dot DW through the width of this trace. This is the width. Again, because we talk about surface current density because we deal with conductors. Remember, charges would go to the surfaces. They stay there. They stay there and they move on that surface. And that causes surface current densities. Mm-hmm.
How about for the surface? Can you explain for the surface?
For the surface current?
Yeah, you say the charges go to the surface.
Mm-hmm.
Then that's when you have the double interval for the volume?
No. Here.
Oh, okay.
The surface current density is, you will hear about it again when we're working with conductors.
Oh.
Conductors, because charges go on the surface, when they move, they also move on the surface. They don't move through volumes. They move through the surface, like this one.
Okay.
Right? Just like a sheet of paper, let's say. If current was going through it, it would look like this. But as opposed to this box, that if current was going through it just like a pipe, it would go through the whole volume.
It's unintuitive because it's like amp per meter and not meter squared.
Yes. It's unlike, when we were talking about volumetric charge density, it was Coulomb per meter cubed, right?
Yeah.
Yeah. Yes. But this one, because J has a different definition, is a little bit. Go ahead.
What does IDL represent? Is it like linear current density, like J?
No, the IDL is going to be the piece that you would find the force on it. Usually, from now on, when we talk about current, we need to talk about which section of current we are talking about, because current by itself is a scalar, right? In order to vectorize it, we associate a length to it, right? I here is I. As you see, there is no J here. I is I, current is current. But because we want to vectorize it, we associate the piece of wire to it. Okay, so I think I already drove this, but yeah, so you can, let's see. So we said if you have a closed loop, B, or FM, is going to be, do you remember what it was? On this closed loop, if I had a current going through here, I. Exactly. IDL cross B. Okay? So that's our magnetic force. Now, we also said that I is dq over dt. So we are doing this. dq over dt, dl cross b. So this is going to be dl over dt is the vector u, du. So it's going to be dq, well, you can say q here, because if it's easier to say, actually, no, sorry. This is dl, this is u, so that's correct. This is u, and then this will be dq u cross b. So macroscopically, when you're talking about the force on a current, or you're talking about on a closed current loop, and you are calculating the force on it, you're talking about the forces that is being applied to every little charges that is moving. along that wire. That's why there is a magnetic force on a piece of current. It's because of they are the moving charges. Go ahead.
Doesn't the current running through the wire generate the magnetic field itself?
We'll talk about it.
So we're not taking it into account here.
No, right now, you're back to fundamentals. Like, we were talking about conventional method would say, if there's a Q here, there's a Q here, there is Newton laws. There is a force that this one applies to. And later we learned that's not true. We don't have forces because charges apply forces to each other. It's because one of them is in the presence of the electric field caused by that one, right? So the same thing here. Why current gets a force on it? Because it's creating a magnetic field. That magnetic field is basically interacting with the existing one, and that's why you would have an interaction, that force between them. Mm-hmm. Okay.
Yeah. Why is it del over dt du? Like, why is it, or is it just?
Velocity is defined as dl over dt, right? You don't need a du for it.
Oh wait, it's like a unit length, so like a unit vector.
I don't think you would need that. But think of it as a small, eventually you're right, dl or the direction of u, when you're integrating over this, it changes. U is not uniform, right? Yeah, it is going to be small, but it is associated with that dq. dqu is basically like idl, right? Yeah, they're together to vectorize it. Okay. Now, what if B is uniform here? So we said magnetic force on a piece of current is IDL cross B, and then if B is uniform, you can take it out of the integral with the operation. And I is, let's say, uniform. So Fm is going to be IL cross B. So you're not integrating, you're just going to apply the lengths and the directions. For example, here, if this is x, y, z, x, y, z, right? IDL or IL cross B, what is the direction?
It's like into the page.
Into the page? Okay, let's see. So we have fingers that way. Yes, exactly. So you would have FM. Oh, sorry, going into the page. Right? It's going into the page. Now, it's saying, what if this piece of wire, it wasn't the, the current, it wasn't the purple one. What if it was the red one? What would be IDL cross B then?
Same thing.
Why same thing?
Because
The red one looks longer.
It's a conservative vector field, so it's, the path integral is path independent. Is that the reason?
Yes, exactly. Even if because you're integrating DLs, right? Even if you didn't know about the vectors, right? Even if you do that, but the reason is, as Nee said, it's path independent. So here you would add all of these little DL vectors, and then at the end, all of the perpendicular directions would cancel each other. So all of the ones that are kind of like in this direction, they would cancel each other, and you would end up with the smallest path, the shortest path, which is that straight line from one to another. So that again, if you're giving, if I tell you to find FM on this current loop, okay? Looks abstract.
Where's the start and end?
Right? So, like, for example, if I say find it from this point to this point, the FM, right? What you can do is consider an eye between these 2 points instead of going through the purple lens. The magnetic force would be exactly the same. Does it make sense? Okay. Now, let's find this. It says a semicircular loop lies in a uniform field B, which is in y-hat direction. Calculate the force on the loop if it carries a current I. Okay? So now we are going to calculate Fm, which is I dl cross B. And then since B is uniform, why is B uniform?
It's just constant.
The amplitude is a constant, it's B naught, right? And the vector is also a constant. Y hat is everywhere, it's the same everywhere. So this is a uniform field because B naught is constant, and then Y hat is a constant vector. Okay? So now we can take this out and say this is I, this is dl, this is cross B, which is B naught Y hat. How do I find this?
I split it into two intervals, one for the first one for the second one, and the first one dl is dx, and the second one I use r and theta.
Exactly. So let's go. We have two sections. dl is going to be on dl of 1 to 2 is going to be dx x hat, and then dl in from point 2 to 1, what would that be? Phi, right?
DL cross B.
But it has to have a length. Yes, r d phi, which is a, d phi, phi hat, right? So now we can say Fm in the total is I, dl from point 2 to 1, dl1, which is dx, x hat. From point 1 to 2, sorry. Point 1, what is dx here?
Wait, sorry, what's the question?
At point 1, what is dx?
Oh, negative. Like,
At point one,
Huh?
0.
This is x equal to 0.
Negative one.
Minus a.
Minus a.
oh, right.
This is a.
Oh, I can see it now.
Okay, guys.
I thought that was a T
Okay, so 1 to 2 minus a to a dx, right? So we have Fm, let's say Fm 1 to 2, and that's how we solve the IDL cross B, which is B naught Y hat. And that is going to be I to A x hat cross B naught Y hat. What is that?
Is that?
Do you remember that circle that we talked about before? X, y, z hat. X hat cross y hat is going to be z hat. Now, let's go to the second part. Fm 2 to 1. That's I. We are moving from point 2 to 1. dl of 2 to 1, which is a d phi hat cross b naught y hat. And here, point 2. At point 2, what is phi?
0.
0 to pi.
0, and point 1 is pi, 180 degrees. So now, can I take this phi hat out of the integral?
Turn it into cosine, what was it? Like minus y comma x.
Can I take it out of the integral? Let's say that first.
It's not constant.
It's not constant, right? Okay. So I can say that this is going to be pi a phi hat. This is not equal to a pi phi hat. Okay? So how can I find the integral of a d phi phi hat?
If r hat is equal to cosine x hat plus sine y hat, then phi hat is equal to minus sine plus cosine. You know what I'm saying?
Yeah, I got it.
Okay, so from 2 to 1, right? What is the shortest length?
It's minus y comma x.
It's going to be minus x hat direction, right? We just learned that if you do,
Oh,
instead of
short
going
span.
on the loop, I'll go shortest distance,
Yeah,
2 to 1, right?
it makes sense to me, because if you split up to its cosine sine, then the
Yes.
y component will be 0.
Yeah, but at the same time, like you can go through all of that, right? Decompose phi hat to two constant x hat and y hat and then do the integral. Or you can say, I already know that from point 2 to 1, this is equal to this. It's equal to I dx x hat from point A to minus A. And that's cross b naught y hat. So that is going to be minus 2ai b naught z hat.
That's what Mo was saying.
Okay, so what is the total field?
0.
So we have zero field, zero force on this. You already kind of, let me see if I can explain. So here, let's draw this, that here, if we said on this section, it's plus z hat, right? Which is coming out of the page. So this is FM12, okay? And then on the second part here, it's going to the reverse direction, which is going into the page here, FM21. Again, we are talking about these 2 points. We are not talking about like 2 different sections. Okay, so we have one side of this going to the page and another one coming out. What happens?
Does that mean that in any closed contour we just get the force of 0?
Yeah.
Depends on the, yeah. Yes. But what happens here?
They cancel each other out at the point.
But they are applied to 2 different points,
Oh, two.
The field is not.
right?
The moment.
Yes. It starts rotating. It keeps rotating till it's completely aligned with the magnetic field.
Complex, like,
That's magnetization.
does this
We had this, right? So
in like
here,
ordinary?
Nice, just to stay with me, okay? So here, instead of dipole moments, electric dipole moments, we have closed currents that act like a magnetic dipole moment for us. Okay, so closed loops are the ones that have basically a moment, and then that dipole moment, magnetic dipole moment, gets aligned with the magnetic field. But we will get there in magnetization, when we talk about materials getting magnetized. Okay. But the total force, yes, it's 0. So, if you wanted, we will continue with this, but I already explained what's happening. Even though on a closed loop, the magnetic force, the total magnetic force is 0, it doesn't mean that we don't have movement. Go ahead.
When you say align with the magnetic field, what do you mean? Like, I thought it would just keep on spinning.
No, it doesn't do that. Okay, let's solve this one then. Okay, let's solve this one. So we have again closed loop, 4 sections, right? So FM here, we have 3 minutes. Yes, we can do this. FM here, I'm going to call this P1, P2, P3, and P4. The total FM is the FM on first. The section that is between P1 and P2, okay, plus FM. This is not multiplication, I don't know how to. P1, P2, FM, P2, P3, plus FM, P3, P4, and then FM, P4, P1, right? Now, since we know it's IDL cross B, and B is uniform, right? So, and DL is already shortest length anyway. So here we say here P1 to P2 DL is basically B Y hat cross B naught, let's call it, this is uniform. It's going to the page, so minus Z hat. And then here we have I. Here from P2 to P3, we have minus A X hat cross B minus Z hat. And then plus P3 to P4 is again minus B Y hat minus B naught Z hat plus I. 4 to, this one is A X hat multiplied by, or cross minus Z hat. Okay, so in each section, current is going this way, magnetic field is that way, right? So FM on this piece is here, P1 to P2. On this side, it's going to be this way. FM is going to be FM P2, P3 is in that direction. And here, it's going to be FM P3, P4. P4 is in this direction, and here we have FM P4, P1. What happens now? Does it rotate?
And yeah, moment and it cancels out.
I don't think it was.
No. The total force again is going to be 0, but you don't have a momentum or a torque either. Okay? Does it make sense? Why did this happen and it didn't happen to this one? Go ahead.
The
directions in this one cancel out, so it just ends up making a 0.
So exactly, you can say if this is my closed loop, right-hand rule again, if I go in the direction of the I, ds, or I am in the surface of I, then there is a momentum called M, magnetic momentum, or magnetic moment. Which is equal to IS, what was it? Yeah, IS, right? And the S here, it's in n hat direction. N hat is the one normal to the surface of the current loop. So here, our n hat, or dipole moment, magnetic dipole moment, is going to be in the direction of z hat. So it's actually I, S, the area is AB, in z hat direction. But our magnetic field is also z hat direction. It's just reversed, right? So if the dipole moment, the magnetic moment, is in the same direction of the magnetic field, no torque. It's already aligned, let's say. Okay? Yes, it's already aligned. It's not going to rotate. So that's why if it starts spinning, it will only continue spinning till it aligns itself with the magnetic field. And as soon as it does that, then the torque is 0, the force is 0, everything is 0. It doesn't move. Okay? Okay, thank you very much, everyone.